Welcome back to part 3 of our notes on general equilibrium. We have already discussed what K is, that is the equilibrium constant. We've discussed how at equilibrium the rates of the reaction are equal. That's the only thing equal at equilibrium. That's the equal part of the word equilibrium. I have said nothing else about anything else being equal other than equal rates of forward and reverse reaction. So be sure that you very clearly never forget that, because they will ask that question on the test in one way or another. And you need to be responding with it is simply the rates that are equal at equilibrium. You may coincidentally have equal amounts of products or reactants. Now, what if I do? What if I have equal amounts of products and reactants? Does that mean I'm at equilibrium? Well, that brings us to this idea that I want to start with today called a reaction quotient, which we symbolize with Q for quotient. Get the idea? Now, quotient would imply some math going on. And check out the math. We take the concentration of our products raised to their coefficients as exponents, and and you're like, hey, that looks just like K. Well, it does get calculated exactly like K. Q is mathematically calculated the same way as K. Q is not the same thing as K. Q is to get a number so that you can look at that number and figure out, are you at equilibrium or are you not? If I have equal products and equal reactants, and it's all coefficients of 1 and that sort of thing, I would end up with an overall term of 1 here. Does that mean I'm at equilibrium if Q equals 1? Well, we really don't know, because what you need to do is find both. Did you hear that? You need both a Q and a K. So you need a number for Q and a number for K, and you would compare them. That did not work, sorry. You need to compare them, so, well, you get the idea. So that if Q is less than K, why would Q be less than K? Less numerator, more denominator than K should have. You need a bigger number, so I need more numerator, less denominator. If Q is less than K, I don't have enough products yet to be at equilibrium, and I have not used up enough reactants yet to be at equilibrium. So what that means is the forward reaction would still be going. That is, we would go from reactants to products. We would continue to do that to drive up the numerator and reduce the denominator until Q equaled K. If Q is greater than K, then we have if Q is greater than K, then we have the fact that our numerator is too big and our denominator is too small, so I need less products and I need more reactants, which means when we look at our reaction of reactants to products, the rate of the reverse reaction will go faster than the forward reaction in order to get to equilibrium. Everything in the world is tending towards equilibrium in terms of chemistry. And you could make a political and sociological equivalent statement, I'm sure. I don't care because it's not chemistry. But everything in chemistry is tending towards equilibrium. Equilibrium is that position of lowest potential energy that everything is going to eventually lower into. That is if Q equals K. So Q wants to equal K. My reaction wants to go in either forward or reverse until Q equals K. If Q is too small, it's going to go more forward and less reverse for a while until it gets to K. If Q is greater than K, to get the numerator of the product smaller and the reactants greater, we actually go in reverse faster for a while. And then we're looking for that point at which Q equals K, and then we are at equilibrium, and my arrows were supposed to be equal size. Okay, so when do you use Q? You use Q anytime. Q would work anytime. You could calculate a Q no matter the situation, you can calculate a Q. When is it a K? When is it in equilibrium? When you know for a fact it is at equilibrium. So if they tell you the equilibrium constant is, guess what? It's at equilibrium. If they tell you the reaction quotient is, guess what? It's not at equilibrium. What if you don't know? Then calculate a Q, and then you can see. Let's do an example. I know you're like, that, I'm not sure that's making sense. It really does make sense. You just have to practice with it. So I have this reaction. Check out what I'm told. I'm told the reaction. There's my R. I'm told a K value. We'll use that in a minute. And I'm told an E. So I'm jumping to the equilibrium concentrations. That's just what's provided in this question. Could they do that? Yes, especially if they want to know if you are going to be at equilibrium or not. If they want you to tell them, are you at equilibrium, they're very likely to just make the math less, which is something they're very likely to do on the test, give you the equilibrium concentrations already. Meaning, do I need a rice table? No, not really. Not at this moment. What I need to do to know if this is at equilibrium is I need to calculate a Q. So Q is products raised to their coefficients. So concentration of products, because there's not pressures, concentration of products raised to their coefficients, they're both ones, divided by concentration of the reactants, and there's only one reactant, raised to its coefficient. And now I'm going to plug in numbers. So I am told on the top 0.280 molarity, and I'm told on the bottom also on the top, those are my two products, and then on the bottom I'm told 0.500 molarity. Okay. Now it's that most fun time of all to calculate. Okay, now have you caught it? Have you caught my mistake already? Yeah, I intentionally left something out so that we could talk about a warning. Guess what students do all the time? They do this part correct, which is great because that alone might be a point out of 2 or 3 for the question. So definitely write that part. But then they substitute in, and guess what? They often forget to bring over. Okay, so be very careful. I'm talking to you. Be very careful about bringing over those exponents, and be sure that you check your balanced equation for those exponents. Okay, it should match all the way through. It's worth that extra 30 seconds on the test to double check that you are, do I have all these numbers represented correctly? Yes there, and yes there. Now we're ready to calculate. So we pull out our calculator, we multiply the numerators, we divide by the denominator squared. Lots of fun going on there. Okay, let's talk about what this means. 3.81 is what I get. Again, no label. So that's my answer for Q. Now we see why we were given KC. Q is 3.81. K was 65.0. The question is, am I at equilibrium? Well, if I was at equilibrium, these numbers would match, so no. I am not at equilibrium. Here's my proof. Now notice on the test, if they ask me this question, here is my proof. I don't do all this on the margins and then write no in the lines of the paper, because this would be a free response type question because you need a calculator for that. I would show all this work for Q, because very likely there's 2 points hidden in this work right here somewhere just to get to the answer of no. They want to see the proof of your statement. Okay, so no, it's not at equilibrium. Now let's ask the next question. What would have to happen to get it to equilibrium? My Q is less than K. And if this helps, if you always put your K, wow, it would help if I didn't mess that up. Let me erase that, sorry. Okay, Q is less than K, and little, I don't know if this is going to help you or not. I'll show you in a minute. Q is less than K. So what needs to happen in order for Q to equal K? I need a bigger number. I need more numerator, less denominator. Since numerator is products and denominator is reactants, which way will my arrow go faster for a while? from reactants to products. Make more numerator, more products, use up reactants. Now there still will be a reverse reaction going at the same time, because that's what happens at equilibrium. There's not a stop to the reaction. It's not a one-way reaction. Both are going. But at this point in time, forward is going to be going faster than reverse because it's still trying to reach equilibrium. It's on one of the two sides of our potential energy graph. It's either, up here falling that way, or it's over here falling that way. It doesn't really matter which way you put it. Now, I wanted to show you this. If I turn my less than sign into an arrow, which way is my reaction proceeding faster? From left to right, which is exactly what I said here. So a little trick, if it helps you, if it confuses you, ignore it entirely. But if it helps you, if you always write K on the left and Q on the right, the sign of your greater than or less than sign will, when turned into an arrow, tell you which direction is the faster reaction. Okay. Now, typically what we're going to do, that's Q, and it calculates the same as K, and it tells you if you're at equilibrium or not, or if the forward reaction needs to go faster, or if the reverse reaction needs to go faster. If my Q was greater than K, hypothetically, if Q was greater than K, it has already passed equilibrium, and the reverse reaction, that's capital K, is going to go faster in order to go back to equilibrium. Okay. Like rolling a ball down a valley like this, okay, the ball is going to kind of wobble back and forth a while before it settles in at the bottom. Same thing can happen in our reactions. It can go past equilibrium, then come back and pass it again, and then come back and then pass it again, and it can just kind of wobble back and forth till it finally settles in to a place of lower potential energy. Okay, this is a super common way that we use equilibriums for. This is a super common question on the exam, so be sure you know how to do this calculation well. Typically, we are given a Kc in our problems, and we're given a reaction. In this case, a generic reaction of A plus B equals C plus D. Check out what else I'm told. I'm told the initial amounts of A and B, and obviously then no amount of products. So I have all reactants, no products. Now, duh question, I know, but which way will this have to travel in order to reach equilibrium in the first place? Well, since I have 0 products in all reactants, it is going to go faster in the forward direction for a while. That's guaranteed. What will be the concentrations once it's finally at equilibrium? That's the question. So check this out. I have my R, my I, my C, my E. And we're going to build a Rice table. Okay. The concentration of A and B, we're going to lose some of A. And we're going to lose some of B. And we're going to make some of C, and we're going to make some of D. Because, again, that forward reaction is going to be much, much, much faster for a while. And in a real reaction, probably starts out fast and starts slowing down as it reaches equilibrium, sort of a thing. But that's a kinetics issue that you could spend your lifetime studying for a reaction. Not something you need to know. What we do need to know is, what are we going to lose? How much of the reactants are we going to lose? We don't know is the answer. So we're going to say, hey, let's lose X amount. Now check this out, because it is a 1-to-1 ratio. Well, I should put the circle there. Because if it's a 1-to-1 ratio, I'm going to lose 1x here, and I'm going to lose 1x here. If I wanted to say 3x there, I'd have to say 3x there. I'd have to maintain that 1-to-1 ratio. That is important. Also, it's a 1-to-1-to-1-to-1 ratio between C and D. So I'm going to gain X amount there, and I'm going to gain X amount here. And so what do I have at equilibrium? Well, that didn't work. Okay. What do I have at equilibrium? I have 0.200 molarity minus X, 0.200 molarity minus X, and I have X and I have X. Okay? No big deal so far. Well, I've simply summed up my columns. That's all I've done. Now let's write a Kc. Kc is equal to concentration of C times concentration of D divided by concentration of A, concentration B, and I'm going to take that 30 seconds to be sure I've transferred in my coefficients. Very, very important. Okay. C. What is C? C is x. What is D? D is also x. What is A? A is 0.200 molarity minus x. And what is B? 0.200 molarity minus x. Check out what we got here. We have a multiplication of these two things. And I bet you thought FOIL was never going to be a useful tool, right? First terms, outside terms, inside terms, last terms. Yay. Okay, actually there's a shortcut, and you should be looking for this. It is extremely unlikely they're going to ask you to do a full-out FOIL or a full-out quadratic equation to solve a problem on the test. Why? Because it proves you know math, not chemistry. It is extremely likely they will give you a way to shortcut it, as I'm going to be showing you several shortcuts throughout the notes. Why? Because that proves you know chemistry and know when you can shortcut it, and it proves when you can't. In fact, in all of the history of the AP Chemistry test, only once have they ever had the need of using the quadratic equation to solve a problem. And they will probably never do that again, because that favors students that have a calculator that have the quadratic equation built in, so all they have to do is type in my A is this, my B is this, my C is this, what's the answers, as opposed to someone who has just a add, subtract, multiply, divide calculator. They want to make it fair for everyone, so even for those students that can only add, subtract, multiply, divide, it's very likely they would not make that happen again. So it's very, 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 very likely that you will be able to, on the test, use some sort of shortcut. Here's the shortcut I'm going to use. I'm going to group my like terms, so I get x squared over 0.200 molarity minus x squared. And you're like, how does that help you? Well, check this out. This is equal to Kc. Kc is equal to 49. And if it bothers you that I've put so many equal signs on the same line, then just skip spaces and rewrite it each time, no big deal. I have a square, and a square. So let's square root both sides. So now I'm going to come over here, x over 0.200 molarity minus x is equal to 7.0. Probably should add another digit, 7.00. Okay. Oh, look, I'm not at all going to need the quadratic equation for this one. This is going to work out pretty well for me. Okay. Let's do the algebra. Yay, algebra. Okay. So I have x is equal to, now I'm going to take this whole quotient here and multiply by the 7. So 7 times 0.2. I want to be sure I'm saying this right as 1.4. Yes. So 1.40 molarity minus, because I like multiply the 7 to the 0.20 as I brought that quotient over here, and I'm going to minus 7.00x. Let's group our like terms. 7.00x plus another x is 8.00x equals 1.40 molarity. So x is equal to, so 1.4 divided by 8. 0.175 molarity. Now notice I do have a label on x. Let's talk about what I have achieved. I would box this, by the way. It always is good on the AP test to box your final answer. It just helps them to know what you are officially terming your final answer. Okay, with that said, what in the world does x signify? Because x would not answer the question. The question was, what is the equilibrium concentrations of A and B and C and D? And x does not tell us anything on its own. They would be like, oh, sorry, you get 1 point for all this work, but you don't get the point for the answer, because I have not officially answered the question. That is x. What is x equal to? Now we come back up here. Oh, look, x is equal to the concentration of C and equal to the concentration of D. So I would actually like to declare all of that to be my final answer there for C and D. Now what about A and B? Well, I have to take 0.200 minus x. So concentration of A, which happens to be equal to the concentration of B, is going to be, well, that didn't work. I'm running out of room. I'm sorry for squeezing it in. You can, obviously on the line pages of the test, you'd have as much room as you want. By the way, if you're working the free response portion of the test and you run out of lines in the test booklet to write in, you can at any time raise your hand and ask for more lined pages. The test proctor has more additional line pages, and you simply write your name on it and you write in your code number that's all over the other parts of the test that you are so tired of filling in by now, and you write what question number you're continuing, and you just keep going, and it gets graded as if it was a part of your test booklet. So anyway, 0.200 molarity minus 0.175 molarity, and I like actually writing that out. It is not necessary to write that out, but I like writing it out because if they, well, that didn't work. Went for my calculator and instead killed everything. Okay, if they can't follow what you're doing, they will not attempt to read your mind, and therefore you very likely will lose points for. Let's try this again. My apologies. You will very likely lose points for things that you think and truly deserve if you do it all in your head, or if you do it on your calculator and don't show them on paper what you're doing. Okay, so always, always, always show your work, show all the steps, because they need to follow along with you. If they lose sight of where you were at, if they don't understand where you get the numbers you got, they're going to assume that you guessed. And you don't get any points at all for guessing, even if your number is totally correct. If I were to sit here and show none of this work, because I'm doing it all in my head, quote unquote, I'm doing it in my head, okay, so you can't do it in your head. If you don't show all this work, then even with the correct answer here, and the correct answer here, which is 0.025 molarity, I'm boxing that, okay, you would get no points, because that would involve, as far as they're concerned, you guessed, and you get no points for guessing. And I know we go through school saying a guess is better than leaving it blank, but you know what? Without proof of why you say what you say, it is not better than leaving it blank on the AP test. It's just the way that they grade. It's the way it goes. So yes, I want you to try. I want you to try on the test. You're not guessing, you're trying, and trying on the test involves showing your work and all the steps involved. Okay, let's try another one. What is the equilibrium concentrations if case of this? Okay, now check out. Why does this seem so familiar? This seems so very familiar because it's the same reaction I just had and it's the same equilibrium constant I just had. So again, a review. For the same reaction at the same conditions, our equilibrium constant should be the same. Okay, let's give this a try because I want to point out something and then you'll have lots of time to practice. Same setup, I have my initial. I don't know how much of A I'm going to lose. I don't know how much of B, but it's a 1-to-1 ratio. I don't know how much of C or D I'm going to make, but it's a 1-to-1 ratio with those. So at equilibrium, I now have 0.3 molarity minus X, and to squeeze it on my slide, I'm going to drop those zeros. We'll put them back in before we answer. Okay. So we start out the same. KC equals, yes, you would want to show your work, write the formula. It's always formula, numbers plugged in, and answer in a box. They need to see that. It's not they want to see it, they need to see that if you're going to get points. Here's my formula. I have double checked that I got my coefficients as exponents. I'm going to plug in. On the top I have x squared, but on the bottom I don't have that anymore. I have this, and that's going to be equal to 49.0. So now my question is it going to do me any good to try to square root both sides? No, I am not going to be able to do that shortcut. Okay, so what shortcut am I going to be able to do? Well, I may not be able to do anything. What I would have to do is I would have to FOIL. I'd have to say first terms, inside terms, outside terms, last terms, that sort of thing. That's what I'm going to do. So this is not going to be fun, I know, but let's start with the bottom there. Okay, so x squared, 0.3 times 0.1 is 0.03. And I'm going to leave off the molarities. I'll put them back in. I'm trying to squeeze it on my slide. 0.3 was first terms. Inside terms is a negative 0.1x. Outside terms is a negative 0.3x, so that's a negative 0.4x. And then x times x is a positive x squared. And that all equals 49. Now I'm going to take this whole quotient and I'm going to multiply both sides by that whole quotient. So x squared equals 49 times 0.03 is 1.47. And negative 49 times 0.4 is 19.6x. And a positive 49 x squared. Now I really do want to put it into quadratic equation type of form. That's something I desire. So we're going to set it equal to 0. That should be a 0 there, sorry. Set it equal to 0. So to get this side equal to 0, I need to subtract an x squared from both sides. So 1.47 minus 19.6x plus, now if I'm subtracting 1 x squared, that's going to make it 48x squared. Okay. Rewriting it. That's all I'm doing. 48x squared minus 19.6x plus 1.47 equals 0. Hopefully that's in quadratic equation form that you recognize, because here's my a term, here's my b term, and here's my c term. Okay. Do not attempt to sit here and try to unfactor like we were taught to do in middle school when they messed with the numbers in the book to be sure they always worked out to be whole numbers, because it ain't going to happen that easily. There's no way this is going to be all whole numbers. Don't even try. Use the quadratic equation, which is, the negative b squared minus, how's that go? Negative b plus or minus square root of 4ac minus 2b all over 2a. Okay, fun stuff, right? Don't even do that. If you're on your homework, you get to pull out your phone, you get to pull out a computer if you're at home, a laptop, a tablet, Google. Go to Google and be like, I need a quadratic equation solver. And one will pop up. And it'll have a field to put in your A, and it'll have a field to put in your B, it'll have a field to put in your C. Don't forget your B here is negative, and C might be negative, A might be negative. Be sure you transfer negatives along with it, and then tell it to solve, and it'll give you two answers. Because remember, quadratics always give you two answers. All right, so what do we do in the end for x? Well, x must be, first off, a positive number. Well, that didn't work. Come on. Okay. So x must be a positive number. So if one of the values they give you is negative, you can immediately ignore it because it's obviously not going to be true. X needs to be positive. However, check this out. We're going to be subtracting x from a 0.3 and a 0.1. So if I had a number bigger than a 0.1, I would also throw that out as illogical, because I can't, if I were to subtract here, I'd get a negative molarity. No such thing exists. So it's got to be a positive value for x from your quadratic equation solver that is less than your smallest initial amount, or you did something wrong. But I would just, if you know you did everything right, I would be like, oh, not going to be that. There should always be one good choice of the two that they give you. And if both of them seem like bad choices or both of them seem like really good choices, you did something wrong. So go back and check. So I'm not actually going to finish this up. I'll let you Google some online quadratic equation solver. But you type it in, you get what your x is, and then you do like we did last time. You build a little chart to answer with. C equals D equals whatever your x is in molarity. A equals B. Oh, A will not equal B. Check this out. We're starting with initial amounts. We can't say that. Don't say that. I said that to point out that we can't say that. We would want A and B, the final concentrations of A and B, to be separate lines in a chart. So A would be 0.300 minus whatever we get for x, and B would be 0.100 whatever we get for x. All right. So that's the way we use k's most often. Of course, we could easily be asked to just calculate a k, as we've done before. We could be asked to tell if it's at equilibrium by calculating a q and compare q to k. That's a possibility. Or we could flat out be given k, like we are here, and asked for what are the concentrations at equilibrium. That is truly the most common way it is done. Probably 75% of all RICE tables are where you know a K and you're trying to find those concentrations. So it's definitely a good skill to practice. We're going to pause here and practice because you need the practice. It is worth practicing. And don't get uptight about using the quadratic equation solver. If you see there is a shortcut, use it. If you don't see it, use the quadratic equation solver. Like just Google it or get one programmed to your calculator or something like that. On the test, you will not need it. I'm going to guarantee it. I could be wrong because I'm not writing the test, but I find it extremely unlikely you would actually be asked to solve a quadratic equation to solve one of these. I'm going to tell you if you end up on a question like this on the free response test where you would need the quadratic equation to solve it, you missed something earlier, go back and see what you missed because it's extremely unlikely that that's going to be the case. Okay, this went a little long, but I wanted to show you several examples of what we do with Q and K, and now we're going to practice, so good luck.